This video will be talking about 5.1.2, which is spring mass systems that are free damped motion. And so we're going to have a new variable that's going to be introduced. Our equation is going to start off like this. And actually this can be written as that right now. I'm sorry, not quite omega squared yet. This is d2x dt2 plus b beta over m dx dt plus k over m x equals 0. Now it's going to be omega squared. I make the substitutions that this is 2 lambda and this is omega squared. And then we can come up with our 3 cases that we had previously for solving linear differential equations of higher order with constant coefficients. So case 1 is going to be when lambda squared minus omega squared is greater than 0. We're going to have distinct real answers. We're going to call this overdamped. And it's going to have a solution x of t. It's e to the negative lambda t times c1 e square root of lambda squared minus omega squared t plus c2 e to the negative square root of lambda squared minus omega squared t. And remember, I'm going to multiply like bases, and I'm going to add my exponents when I do that. So number 2, case 2 is going to be when lambda squared minus omega squared is exactly equal to 0, and that's called critically damped. And that solution is going to look like x of t is equal to e to the negative lambda t times c1 plus c2t. And case 3 is going to be when lambda squared minus omega squared is less than 0, giving us complex solution that's going to be underdamped. And we have x of t is going to be equal to e to the negative lambda t times quantity c1 cosine of, now the order is going to switch, so this is positive, so this is going to be omega squared minus lambda squared t plus c2 cosine of omega squared minus lambda squared t, like that. Again, just like before, the omega squared minus lambda squared or lambda squared minus omega squared is kind of new, but it just stands in the place of that. It's basically in the place of that beta that was in the problem here. Lambda stands in the place of alpha, so on. So, and alpha and beta together make what used to be m, but we're not using alpha and beta because beta is up here in the problem as our dampening force. I'm also not using m's in the problem because m is already in the problem as my mass. So I'm not doing the substitution. I'm just going to go ahead and jump straight to the equation. So let's go ahead and get started, starting with number 25 here. And it says a mass weighing 4 pounds is attached to a spring whose spring constant K is 2 pounds per foot, and the medium offers a dampening force that is numerically equivalent to the instantaneous velocity. So that means that my beta is equal to 1. The mass is initially released from a point that is 1 foot above equilibrium with an initial velocity of 8 feet per second downward. So that's a positive 8 feet per second. Determine the time which the mass passes through equilibrium. So let's find our equation for the spring motion here. So we have 2 lambda is going to be equal to beta over m. So 2 lambda is going to be equal to 1 over, and m is going to be 1/8 of a slug. So lambda is equal to 1 over 1/16. Lambda is equal to 16. Sorry, this is 2 times an eighth, 1 over a fourth. Lambda is 4. Lambda squared is 16. Misspoke. All right, omega squared is k over m is k is 2 and m is an eighth. So omega squared is equal to 16. They're equal, so it's case 2 critically damped. And if I need it, omega is going to be equal to 4. So x of t is going to be equal to e to the negative 4t times c1 plus c2t. That means that x prime of t is negative 4 e to the negative 4t times c1 plus c2t plus c2 e to the negative 4t, which is going to be equal to e to the negative 4t times negative 4c1 minus 4c2t plus c2, which is equal to e to the negative 4t, negative 4c1 plus c2 minus 4c2t, and x of 0 is going to be equal to e to the 0. C1 plus 0 is C1, which is going to be equal to negative 1. And x prime of 0 is going to be equal to e to the 0 times negative 4c1 plus c2 . That's going to be equal to 8. And c1 was negative 1. So negative 4 times a negative 1 plus 2 equal to 8. 4 plus c2 is equal to 8. c2 is equal to 4. And we have x of t is equal to e to the negative 4t times c1 is -1 plus c2t. Now that I have that, I can find where the mass passes through equilibrium. So find when x of t is equal to 0. So that's going to be when e to the negative 4t times -1 plus 4t is equal to 0. Well, e to the negative 4t can never be equal to 0. It's an exponential function that has an asymptote at y equals 0. So it's got to be the -1 plus 4t that equals to 0. 4t is equal to 1. And t is equal to 1/4, and that's in seconds. Second part of the question says, find the time at which the mass attains its extreme displacement. So that's going to be find when x prime of t equals 0. So that's going to be e to the negative 4t times -4. So that's 4 plus 8 is going to be 12. Plus -4 times 4 is 16. This is, let's go back here. So this was -4 times, and then C1 was -1, plus C2 was 4. There we go. Minus 4 times C2 was 4t. That is what x prime of t has to equal. And so that equals e to the negative 4t times, so 3 times -4 is -12. Then this was -4 C1 plus C2. Sorry, missed a parenthesis there. So -4 C1 plus C2, that's 4 plus 4 is 8, minus 16t. There we go. All right, let's go ahead and set that equal to 0. So that again is going to be when this part in parentheses is equal to 0. Which can be when -16t equals -8, when t equals 1/2, and that's in seconds. That's when it reaches maximum displacement. This is equilibrium. This is max displacement. And then it's going to ask what is the position of max displacement. So that's going to be x of 1/2 is going to be equal to e to the -2 times -1 plus 4 times a half is 2. 2 minus 1 is 1, so that's going to be e to the -2nd, which is about 0.14, and then this is going to be measured in feet. Good warm-up problem. Let's go ahead and move on to number 27. A 1 kilogram mass, so we actually have a mass here. 1 kilogram is attached to a spring whose constant is 16 newtons per meter. The entire system is then submerged in a liquid that imparts a dampening force numerically equivalent to 10 times the instantaneous velocity. Determine the equation of motion. Okay, so if I need the weight here, mg, that's going to be 9.8 newtons. Doubt I'm going to need that, but let's go ahead and find here that it says part A, the mass is initially released from a point 1 meter below equilibrium, released from rest. So 1 meter below equilibrium position. Let's find the equation based off of that. So 2 lambda is equal to beta over m. So lambda is equal to beta over 2m. Lambda is equal to 10 over 2 times 1 is equal to 5. So lambda squared is 25. Omega squared is k over m. Omega squared is 16 over 1. Omega squared is 16. So we have lambda squared minus omega squared is 25 minus 16 is 9 is greater than 0. So we are overdamped. And we have x of t is e to the negative lambda t times c1e to the, let's just go ahead and fill in my numbers here. So lambda was 5, e to the negative 5t times e to the square root of this difference. So that's the square root of 9 is 3t, c1 e to the 3t plus c2 e to the negative square root of 9 is 3t. Let's simplify that. X of t is equal to c1 e to the 3 minus 5 is negative 2t plus c2 e to the negative 3 minus 5 is negative 8t. Makes x prime of t pretty easy to calculate. It's going to be a negative 2c1 e to the negative 2t minus 8c2 e to the negative 8t. X of 0 was c1 plus c2, and that's 1. And then x prime of 0 is negative 2c1 minus 8c2, and that is 0. Multiplying the first equation by 2, I get 2c1 plus 2c2 equals 2. Let's go into setup for elimination here. I get negative 6c2 is equal to 2, and c2 is equal to a negative 1/3. With c2 being a negative 1/3, then c1 minus 1/3 is equal to 1, and C1 is equal to 4/3. That gives me x of t as a C1 is 4/3 e to the negative 2t, and then C2 is a negative 1/3 e to the negative 8t. Part B asks me if the mass is initially released from a 0.1 meter below equilibrium with an upward velocity of 12 meters per second, then what is the equation? So part B says instead that x of 0 is still 1, and x prime of 0 is negative 12 meters per second. Okay, so the only thing that's changed here is my equations now say C1 plus C2 equals 1, and negative 2C1 minus 8C2 is equal to negative 12. So again, I can multiply this top equation by 2, get 2C1 plus 2C2 equals 2, negative 2C1 minus 8C2 equals negative 12. And that sets me up for elimination to have negative 6C2 equals negative 10, and C2 equals 5/3. C2 is 5/3, then C1 plus 5/3 is equal to 1, which is 3/3, and C1 is negative 2/3. So x of t in this case would be a negative 2/3 e to the negative 2t plus 5/3 e to the negative 8t. Moving along to number 29. A force of 2 pounds stretches a spring 1 foot. So F equals KS. 2 pounds equals K times 1. So K equals 2 pounds per foot. Mass weighing 3.2 pounds. So that is going to be 0.1 slugs. Is attached to the spring, and the system is then immersed in a medium that offers a dampening forces numerically equal to 4/10 times the initial velocity. So B beta is 4/10. And we want to find the equation of motion if the mass is initially released from rest at a 0.1 foot above equilibrium. So we have, let's find our lambda, which is 2 lambda is beta over m. So 2 lambda is equal to 0.4 over 0.1 to lambda is equal to 4, lambda is equal to 2, lambda squared is equal to 4, and omega squared is k over m. So omega squared is k is 2, m is 1/10. So omega squared is equal to 20. You definitely see that omega squared is bigger here. So lambda squared minus omega squared is equal to a negative 16 is less than 0. So this is underdamped. Case 3. Now we're going to have an equation of motion, x of t is equal to e to the negative lambda t, that's negative 2t times c1 cosine of, so switch this order here, that's a 16, square root of 16 is 4t plus c2 sine of 4t. And then when we take the derivative of that to get our velocity equation, x prime of t is equal to negative 2 e to the negative 2t times c1 cosine of 4t plus c2 sine of 4t, and then product rule, so plus e to the negative 2t times, and then this is going to be negative 4 sine, negative 4 c1 sine of 4t. Let's just write that down here. Plus e to the negative 2t times negative 4 c1 sine of 4t plus 4c2 cosine of 4t. And let's combine all that. So x prime of t is equal to e to the negative 2t times a negative 2c1 cosine of 4t plus a 4c2 cosine of 4t. And then this is going to be plus a negative 4c1 minus 2c2 sine of 4t. Negative 2, positive 4, negative 4, and positive 1. There we go. There's a plus 1 C2 right there. That's where that 1 is. Okay. And then we have x of 0 is going to be C1, which is going to be negative 1. X prime of 0 is going to be negative 2c1 plus 4c2. And we're starting from rest, so that equals 0. Since c1 is negative 1, 2 plus 4c2 equals 0. 4c2 equals negative 2, and c2 equals negative 1/2. So that is an equation x of t is equal to e to the negative 2t times negative cosine of 4t minus 1/2 sine of 4t. And that was part A. Part B says express the equation of motion in the form of, and they give you a form here. Let me go ahead and write that out. So part B says express the answer from part A in the form x of t is equal to a e to the negative lambda t sine of omega squared minus lambda squared t plus phi. Should look familiar. We did something similar to that last time. A is still going to be square root of c1 squared plus c2 squared, which is going to be square root of -1 squared plus -1/2 squared. It's square root of 1 plus 1/4. Square root of 5/4 is √5/2. And I'm just going to look here and see, because they're both negative, we're in quadrant 3, meaning that sine is going to be negative, cosine is going to be negative, and tangent is going to be positive. So I'm going to have to add pi to my answer for phi in order to get into the correct quadrant, because arctangent is going to return an answer in quadrant 1. So when I take tangent of phi and set it equal to c1 over c2, then phi is going to be equal to pi plus arctangent of 2, which is going to be approximately 4.249. And that means that x of t is going to be equal to √5/2 for A, e to the -2t. Lambda hasn't changed. Sine of omega hasn't changed. 4t. And then this is plus 4.249. For part C, they want us to find the first time which the mass passes through the equilibrium heading upwards. So to do that, we're going to take this equation set it equal to 0. And I'm going to get a generic solution here. And we have sine of 4t plus 4.249 is equal to 0. So that means that 4t plus 4.249 is equal to n pi, and 4t is equal to n pi minus 4.249, meaning that t is exactly equal to n pi minus 4.249 over 4. Because time has to be positive, n has to be greater than or equal to 2 here. But I'm going to have negative time if n is 0 or 1. So 2 is my first cycle. It's being pulled down by gravity. It's going to go through equilibrium because I started above the equilibrium point that x0 was a -1. So I go through equilibrium, then I reach my maximum displacement at the bottom, and the spring starts to come back up and comes through equilibrium when n equals 2. So when n equals 2, I'm sorry, 3, because n equals 2 is when it's on its way down. So when n equals 3, it's on its way up. So that t is going to be about, and you can figure this out with your calculator, 1.294 seconds. Number 31 will be our last one in this particular section. It's just kind of a summary of everything. So a mass weighing 10 pounds. It's equal to 10 over 32 slugs. It's equal to 5 over 16 slugs. Okay. Stretches a spring 2 feet, so S is 2 feet. Mg was 10, so 10 equals Ks. S is 2. So K is equal to 5, and that is pounds per foot. And lambda is going to be equal to 2 lambda is B over M. So 2 lambda is, they just tell us that beta is equal to itself here, where beta has to be a positive number. So this is going to be beta over 5/16. So 2 lambda is equal to 16 beta over 5. Lambda is equal to 8 beta over 5. So lambda squared is 64 beta squared over 25. And omega squared is K over M. And omega squared is K is 5, M is 5 over 16. So omega squared is 16. And I want to know when it's overdamped. So question A is, when is lambda squared minus omega squared greater than 0? Remember that beta has to be positive. So let's solve that. 64 beta squared over 25 minus 16 needs to be greater than 0. And I'm just going to multiply everything here by 25 over 64. To make this beta squared minus, and then 25 over 4 is greater than 0. Since beta has to be positive, I'm only interested in the positive square root if I set that equal to 0. So beta needs to be bigger than 5 halves for that statement to be true. And then the 5 halves doesn't change for the rest of these. So next question is, when is it critically damped, which is when is omega squared minus omega squared equal to 0? Well, that's when beta is going to be equal to 5 halves. And then when is lambda squared minus omega squared going to be less than 0? Remember that beta has to be positive here. So beta has to be between 0 and 5 halves. Less than 5 halves, but bigger than 0. So that's it for this section of problems. We'll come back next time and talk about some more problems in talk about 5.1.3, which is still spring mass systems, but it's driven motion. So talk about that one in our next video. See you next time.